Guys, I crafted a beautiful solution for this problem. So basically last night I was trying this problem but I couldn't really get nowhere and I slept. And this morning I was trying and then I found something beautiful in this problem while solving it, and I really liked my solution. Then that's why I want to share this with you guys. Okay. So how do we begin this problem? Yeah. So the one of the ways I thought of is to use King's rule or something like that, but like since there are axes, that didn't really work. And I thought of like factorizing this expression over here. And this gives me x plus I sin x, x minus I sin x. Yeah. And I now try to search for how to express numerator in terms of these expressions in denominator. Yeah. And in that search, like what I found is, if I just try to differentiate this expression and multiply with this one here, I basically will have I cos x and also here x, so that gives me x cos x over here. Yeah, and similarly over here that's 1 and minus I sin x, that gives minus sin x over here. So maybe if I differentiate one of the expression and keep other as it is, that will somehow connect. I thought like that, and I tried to see what happens. 1 plus I cos x and then x minus I sin x. Yeah, and now while multiplying x and then minus I sin x plus I times x cos x and then plus I square and then minus, that becomes plus eventually sin x cos x. Okay, so we get this expression. Yeah, now over here if you notice that the imaginary part is actually the expression that's there in numerator, x cos x minus sin x. Yeah, yeah, so that's why now there's something beautiful. The beautiful is that the imaginary product, imaginary part of this product is actually the expression x cos x minus sin x, and maybe that can be helpful. Yeah, and so after finding this expression, now if I write this expression over here as imaginary part of this product, that can be helpful. I thought like that and I tried proceeding. So if we proceed, what do we get? Integral from 0 to pi by 2 of imaginary part of 1 plus I cos x, x minus I sin x. Yeah, and then by x square plus sin square x dx. Yeah, now since this complex number is divided by real things, yeah, so we can take imaginary part outside and apply this to the whole fraction, because dividing by real part, we can take real part inside the imaginary part function. Yeah, and these real things. Okay, also we can take imaginary part outside the integral, that doesn't really matter, so let's take the imaginary part outside the integral also, and then because that works. Yeah, and now after this let's try to factorize the denominator, and we know that we will get this expression and that cancels out, and this is just derivative. So you see now that's really helpful, and when I noticed it, I was really happy because now it was going to be solved. Yeah, and then x minus I sin x by x plus I sin x, x minus I sin x dx. Now let me cancel this expression, and only this remains. And we know that the expression in numerator is just derivative of the expression in denominator, so that's why we can directly say that this integral is actually log of x plus I sin x. Yeah. And this needs to be evaluated from 0 to pi by 2, but we can do that after taking the imaginary part. That will be helpful for us, like to evaluate the limit condition, because if we first apply these limits, there will be some sort of indeterminants that will make problems. So first of all, we'll try to find the imaginary part and then do the limits. Now imaginary part of this function, what is this? So we know that if we have to find log of a complex number, this is actually equal to log of the magnitude of this expression plus I times argument of this expression, argument of a plus ib. Yeah, you can see this by changing this number to the polar form and then take the log. Yeah, and here the imaginary part is actually argument and the real part is the log of modulus. So we are asked for the imaginary part, so that will actually be argument of this, and we know that argument is just tan inverse p by a. So argument will be tan inverse sin x by cos x, sin x by x. Yeah, so this is the imaginary part of this log of this expression, and this is from 0 to pi by 2. Yeah, and now at pi by 2, this is 1 and this is pi by 2 itself, so we have tan inverse or 2 by pi, yeah, minus at 0. Basically we can try to evaluate this at a limit condition, not exactly at 0 but at 0 plus, and that it is still fine. And at 0 plus this is just 1, yeah, sin x just 1 and tan inverse 1 is pi by 4, and this is the answer. Yeah, so here we basically made that thing that limit x goes to 0 and not exactly at 0, because that's still fine for the integrals. And yeah, we solved this problem. The solution development, I think it was a nicer one. Let me know like how did you find, and like do you also have any alternative solutions? Please let me know in the comment section. I would be happy to go through them. And yeah, to talk about the flow, we first factorized and saw that differentiating one of them gives the imaginary part as original function, and then did that. And now there was cancellation. We took limit, took imaginary part, and substitute the limits. That solved the problem. That was it. Thanks for watching. Hope you enjoy the integral and look forward to seeing you in the upcoming videos too.